Everything truly great requires focus and determination, preparation and drive. It's a calculation of courage, capability, and conviction, all aiming toward the best path forward. Here at Mcdermott, we have a vision. It is driven with purpose. It is maintained with the highest values, unparalleled by any. We are one unified organization. Our vision is one. We proudly create and deliver complete, innovative solutions as the trusted global partner, enabling our customers to maximize the potential of natural resources. We rely on 5 company values, 5 constants that strengthen every corner of our business.
One team. We are one company.
Where everyone is equally important. Well-being. We promote all forms of well-being.
Commitment. We are reliable
and dependable in delivering quality solutions.
Integrity. We maintain a firm adherence
to legal and ethical conduct.
Go beyond. We seek
courageous and creative solutions.
Our vision is a roadmap to realize our potential as a premier, fully integrated provider of engineering, construction, and technology solutions. Our vision is one.
Good morning, good afternoon, everybody, and thank you for participating in this conference. My name is Vaseem. I'm the Global Vice President for Operations and Digital in Mcdermott. I'm also the head of the energy transition and the new energies business. So just a few words about Mcdermott before I go into the subject. So Mcdermott is a US-based, we are actually based in Houston, engineering services company. We design and build and deliver energy projects globally. As I said, we're headquartered out of Houston, but we've got offices in Europe, the Middle East, as well as the Far East. We also have fabrication yards on all continents, and we also have a marine fleet which we use to install some of the facilities we built. The talk today, what I'd like to talk about today, is a subject very close to my heart. It's taking the digital twin from design into operations. And what I always tell my young engineers is that before we come up with a solution, we have to really define what the problem is. So what I'd like to do is start by defining the industry problem. What you see here is what I call the EPC highway. So EPC is engineering, procurement, and construction. So this is the design, the buy, and the build of a project. So what is the challenge in a complex, bespoke, energy transition or traditional oil and gas project? We all start with engineering. We engineer, we procure, we fabricate, we build, we construct, and we commission, and then we operate the facility. The challenge, of course, is that this whole process is not a linear process. Information, activities do not flow in a single direction. Engineering is what you might call a central station. It's a centrale, let's say, in Europe, and it's where all activities originate. And engineering feeds into procurement. The procurement folk buy and they deliver material to the fabrication yard or the construction site. The fabrication and the construction teams build the facility. We commission and we go into operations. The challenge, of course, is that information does not flow in one direction. Information flows backwards in terms of vendor information is required for engineering. Fabrication schedules are required so that we know which sequence the material should be delivered in. And the challenge in our industry is that over the last couple of decades, as the projects have become exceedingly complex, where they have grown from $200-300 million projects to multiple billion-dollar projects. An LNG facility today is well north of $10 billion. As these projects have become more complex, our ability to deliver projects, by our I mean the industry ability to deliver projects on budget, on schedule, has decreased dramatically. There is a recent survey of projects over $1 billion done over a decade, over the last couple of decades. And that survey reveals that 3/4 of projects are late and almost 2/3 of projects overrun their budget. And when you combine the two factors, these statistics show that projects more often than not are delivered late and or over budget. How do we use, the question today is how do we use technology to better deliver the project? So as the title of this series of talks today is how do we use Industry 4.0, Energy 4.0 to better deliver projects? So what I'm going to describe over the next few minutes is how Mcdermott is choosing to use technology and how we believe the industry is using technology to better deliver projects. So I'm going to try and keep this very simple, not go into too many technical details. So the left-hand side is what we call our normal Enterprise 2.0 system. Effective execution of projects requires a cross-functional team effort. It requires engineers, mechanical engineers, process engineers, instrument engineers. And we deliver, these engineers, this team deliver not only deliverables in the form of documents, drawing, work packages, and 3D model, but they also have to interface and collaborate between other parts of the project team. So at a very high level, what do? We design, we buy, we build, we erect, we install. And we use this using tools which are very industry standards. We use 3D software tools like Hexagon or Aviva E3D or Bentley, and we use these tools in an integrated manner. However, these tools do not solve all of our problems. What is missing in these tools which create a 3D model is our ability to create a 3D twin. And why do I distinguish between the two? Because what is missing is the work process behind how we build our projects. These 3D models will give you a status of the facility as of that point in time. But what does not give you is the information required to actually execute a project, the work process required to execute the project. So before I go into the right-hand side, let me just give you a small definition. So what is information? Information is data in context. We need data, but we need data in a contextual form so we can achieve an actionable insight into that data. And that is the right-hand side. That is our collaboration tool, what we call Gemini XD, which is a tag-centric tool. Again, I don't want to go into too many technical details, but a tag-centric tool means that every work process, every action is tied back to a tag. A tag can be a valve, it can be a piping spool, it can be a compressor, it can be a heat exchanger. And what this does is it allows information to flow to the right person at the right time. Because what we're trying to do is identify hiccups in our work processes. We're trying to identify risks early. We're trying to improve our productivity, and we're trying to develop advanced analytics which allow us not only to build a facility, but also to know what problems are we coming up with ahead of building the facility. So Gemini XD is our digital twin. It is our project delivery model. So what is this project delivery model trying to do? Again, the left-hand side is project delivery phase, and the right-hand side is project operations phase. And before I go into this, I need to point out that a lot of what I'm going to be talking about is some of it is deployed and some of it is ready for deployment. So in other words, we are not quite there yet. So on the left-hand side, we are building a 3D model. That 3D model traditionally has engineering information embedded in it. And in some cases, we also embed vendor information into that 3D model. But what we're trying to do is to build into it progress information as well. So the single source of truth during project execution phase, during when you are building a project, is going to be our 3D model, which is the actual parametric model with the Gemini XD PLM built on top of it. So we are coding, all of our material will be RFID or barcoded. That material, when it arrives on site, it is scanned and it is then picked up by the model. So the 3D model will tell you the status of the material. It'll tell you whether it is under order, it'll tell you whether it is under inspection, under delivery, whether it has arrived on site, and whether it has been installed. So all significant material will have an RFID or a barcode associated with it. It will also give you progress. The progress is not only in engineering, which is relatively straightforward to do, but also in fabrication. It will tell you how many spools have been prefabricated, how many have been NDT'd, and so on. So what are we trying to do is to create a single source of truth, which is read from a 3D twin. To build on a reasonably large project, the effort required to build a 3D twin is well in excess of 1 million man-hours. When a project moves from project execution through to project operations, that 3D twin invariably in the industry is shelved. It is handed over to the client, and the client typically would use it, or the operator will typically use the 3D twin to upgrade their facility, to do retrofits, brownfield work, and so on. But what it is not really being used for as the nerve center for information flow in an operating facility. So what we are advocating, what we are designing in collaboration with a number of companies we work with, is to use the same 3D twin, the digital twin, as the single source of operating truth. So as the plant matures, maintenance history is going to go into the 3D twin. It is not going to go into filing cabinets or a separate database, but into the 3D twin. So when you access a heat exchanger, not only are you getting engineering information of the heat exchanger, but you're also getting maintenance information, all tied together. You're also getting operating history. You're also getting analytics. You will be able to see from the digital twin, how the heat exchanger has performed over the last 5 years. Under what conditions is fouling of the heat exchanger increased? Now, once you can do that, you can then also predict when fouling on the heat exchanger will occur, or be able to predict that under what conditions is the seal on my pump more likely to fail, which will then allow, if you go to the 2 o'clock position, early intervention and the ability to log the intervention. You will also use it to develop and maintain your operation and maintenance plan. So when you sign off on an inspection record, you can then insert that inspection record into your digital twin. So what are we trying to do is create an ecosystem where all sources of all information is accessible from a single place. It's not residing in the single place. So for example, the digital twin will have a link, will have an app which goes into the plant or the facility or the operator's SAP or Maximo or the Oracle system. So financial data will continue to reside where financial data normally resides. Marketing data will continue to reside where it normally resides. But information will flow in 2 directions. So that is broadly the vision of a digital twin which integrates seamlessly from early development, from FEL 1, FEL 2, through FEED, through EPC, into the operations of an asset. So what I'd like to conclude with is a small example, just a small sample of what we see technology allowing the industry to do. So this is a bit complex, it's a bit busy slide, so I'm going to take this slowly. And what I'm going to do is focus on the key themes first, which is at the bottom of the slide. So what are we trying to do is to use advanced analytic capabilities to drive continuous improvement in operation. And what are we trying to do is integrate advanced process simulation with the digital twin thus integrating operations with a digital twin. So let's start from the bottom left. This is typically the process simulation model, and my apologies for getting overly technical. The process simulation model is what you build at right in the beginning of a project. This is a digital twin, but it's a very preliminary. It's the skeleton digital twin. It's a digital twin which gives you a very high level indication of how the plant will operate. The process model is then used to develop hydraulic simulations. So this will allow you to size equipment. It allows you to say that this optimum size of the pipe is 6 inch, and the optimal heat transfer surface I need in an exchanger is X, and the optimal head we need is Y, and so on. So this will allow you to do that. At the same time, you are using process simulation to develop your digital twin. But once you're in operating phase, once you're operating the facility, you also have access to plant data, actual plant data. With the actual plant data, you can take your advanced process simulation, you can take your process simulation, you can take your hydraulic simulation, you can take your dynamic simulation model, and then fine-tune the model. The dynamic simulation model is theoretical. You can use this theory and actual data to fine-tune the model, and then you can use that fine-tuned model, a model which replicates the actual parameters of operations, to create what-if scenarios. What if I increase the pressure? What if I change the crude input? So what if instead of buying crude from supplier A, I buy crude from supplier B? What does that do to my products? Does that allow me to produce a different range of products at a different price point? All of this is enabled by marrying design twin with an operating twin. And with this, we can better operate our plant, and we believe we can better maintain our facility. So what are we trying to do is use technology available today to be able to facilitate improved design, improved certainty in delivery in the project phase, and of course, improved operations, safer operations, more profitable operations once we go into the operating phase. The heart of what we're doing is to use what a product lifecycle management tool, which is very common in the manufacturing industry. It's used extensively in aerospace, in manufacturing, in automotive, and so on. And broadly, a product lifecycle management tool is the process of managing the entire lifecycle of a product, from inception through design, through manufacturing. But it's used typically in manufacturing. What we are trying to do is to use PLM software to develop a project lifecycle management tool which can manage the lifecycle of a project from inception through design, through commissioning, into operations, and eventually into retirement. So, big picture, we want to bring life to a static 3D twin that we build in the operation in the design phase, and be able to use it in the operations phase to better operate and better maintain our facilities. Thank you very much, ladies and gentlemen. I think we will now take any questions that you might have. Thank you.